Okay, well, today we're going to talk about planets. Okay, and I love this story. I've talked about this story a lot. Most of you know I have strong opinions about what we mean when we say the word planet, especially with regard to Pluto, but we'll leave that for another day. But today I want to talk about planets, what we mean by planets here in our own solar system, but also what we mean by planets outside our solar system. And this is something that's very new and very much the frontiers of research in astronomy. So it's a kind of exciting and neat topic to talk about. So as always, the slides are here. The previous ones are all up, and then I'll get this one up this weekend. So I'm going to start by talking about the age of exploration, which was a long time ago, and talk about the parallels between that time and today as well. We'll talk about finding other worlds, both long ago and today, and really what it means in terms of planets here, near at home, as well as planets that are far from here, far from home. Okay, so that'll be the scope of the talk today. As always, there's lots and lots of things we could talk about, and we could talk about this for the entire year and never get through all of it. So we're just going to, as always, talk about the high points, and there will be things you're interested in, things you may still wonder, and you should certainly chime in and ask those questions or grab me and we can talk about stuff in more detail later if you want to. Okay? What's this a picture of? Yeah, it's a picture of Illinois, right? This is Chicago, right? Here's Lake Michigan. This is Milwaukee and Indianapolis and St. Louis. This is the United States, the central United States at night. Okay, you see the atmosphere here. You can see the faint glow of the aurora in the north, right? So you and I live in an age where pictures like this don't even faze us. You and I live in an age where information is instantaneously available at our fingertips through magic devices that all of us carry around in our pockets, okay? And it's very hard to remember what the world was like long, long ago. For all of us who grew up in the space age, which is all of us here in this room, it's impossible to know what it was like to live in an era when we didn't know what the world looked like from this viewpoint. Okay, but that's where I want to start today. I want us all to throw our minds backwards and try and put ourselves in the mindset of an ordinary citizen or a scientist or anyone in that time in history when we didn't know this is what the world was like, when we weren't all intimately connected by roads and strings of lights and instant internet communication. So let's go back to 50 years before the invention of the telescope. Okay, so when was the telescope invented? The astronomical telescope, I should say. Early 1600s, 1610. So let's go back to the mid-1500s. Okay, and this is a time when the world, from the viewpoint of Western culture, was just being discovered for the first time. Okay, so this is a map from that time. This is what, so I'm a cartophile. I love maps. I collect maps. Maps are the most awesome things in the world. Okay, that's a result of reading too much Tolkien when I was a young child. Okay, but this is a map from that age. This is a very famous map by Ortelius in 1570. And what I love about this map is that it shows the world from our perspective as modern people. It's easily recognizable as the Earth. But the map simultaneously captures what I call the frontier of everything that we know, but also our ignorance at the same time. Okay, and there's many examples of that you can see on the map, but let me just point out a couple to seed our conversation. So right down here, okay, so this is South America. It clearly doesn't look like South America. Okay, but there's parts of it that do, right? So this eastern coast very much is recognizable as the eastern coast of South America. Okay, but I want to focus on right down here. Okay, so right down here, this is the southernmost tip of South America, which Magellan was the first European explorer to round in 1520. Okay, and when Magellan found his way through there, he found his way through an area called the Straits of Magellan. That's what we call it today. And it's actually the southernmost coast of South America that goes through an archipelago called Tierra del Fuego. And the largest island in Tierra del Fuego is called the Isla Grande. Okay, and that is this right here on this map. And you see it says right there, Tierra del Fuego. Okay. At the time that Ortelius made this map, they knew there was a way around the southern tip of South America. And they knew that Magellan went through the Straits of Magellan, and to his left side was this landmass that is part of Tierra del Fuego. But he had no clue that it was an island because no one had been farther south than Magellan. Even 50 years after Magellan did it, no one had been far enough south to be able to tell Ortelius, this is not part of something much, much larger. And so the map shows that this is a way around South America, but it also simultaneously shows we have no freaking idea what's south of there. Okay, all this blank space, this is as far south as anyone had ever been. That's why it's blank. And you and I look at this map, and if you're not paying attention, you'll be like, oh, well, this is probably Antarctica. Well, sure, Antarctica's down there, but this is not the shape of it. It's way down here, okay? So this is the boundary of our ignorance about what the world looked like. But you don't have to go far from Europe, which is where Ortelius made this map, to see that your ignorance is very, very strong. So let's go up here to Europe, okay? So this is the northern part of Europe, where you have Norway, Sweden, and Finland. And this part of the map is pretty accurate. This part up here, not so much, okay? So even close to home, they had never mapped out that part of the peninsula that contains Finland, Norway, and Sweden accurately enough to make it accurate on this map. Over here, this is the Black Sea. And those of you who've seen maps of the interface between Europe and Asia, that looks almost like the Black Sea. This is the Caspian Sea. That doesn't look anything like the Caspian Sea, right? Okay, they knew there was a body of water there. They had no idea what the shape of it was. Okay, so the map shows us the frontiers of exploration, but it also at the same time shows us where we need to do some more work. Okay, and this is always the case in science. And when we talk about planets, this is really the case. So this is what enabled this, right? What enables us to make a map like this of Ortelius's is technology, right? The only reason we know that you can get around South America is because at some point in time, someone had decided that you could build something more than a birch bark canoe that was capable of traveling across the sea, of carrying supplies, of weathering storms, and making the circumnavigation of the world. Okay, so technology always is the thing that enables you to expand the frontiers of exploration. Okay, and that'll be something that we talk about with regard to planets as well. You've all been up on the floor. Okay, you recognize this? Okay, when was this globe made? Annie? It was made in the 1950s, okay? This globe was made in a time before we had ever flown in space. And when you go look at this globe, there is nothing you see on that globe that looks unfamiliar, that looks the wrong shape, that makes you go, hey, there's no mountains in this part of Asia, right? Everything on this globe was discovered with technology here on the surface of the Earth. With feet, with cars, with boats, donkeys and mule trains, camels, go-karts, okay? All of that was mapped out on the surface of the Earth. But the result of that was a picture that you and I are completely familiar with today because I just have to go up in a rocket and take one picture, and I can see this is what the world looks like, right? When the astronauts flew to the moon, okay, so if you stand outside the circle here, you have the same view that an astronaut would have if they were 8,000 miles away from the Earth. Okay, so the space station flies at about 300 miles or so, 300 kilometers, 300 miles, one of those, okay? So we never go farther than that right now. Only the Apollo astronauts have ever seen the Earth from this view. But every single one of us has seen that picture because in the age of the internet, every picture that Apollo ever took has been digitized and is circulated on Facebook regularly every 2 or 3 weeks. And so we're familiar with it. We forget that there was a time where it was hard to make this map. It was hard, not just to make a map, but to discover the world itself. Which is a little mind-blowing when you sit and lay there late at night thinking about it. Okay? So, let's talk about the discovery of the worlds. Okay? So, all of the naked eye planets have been known since antiquity. right? They've been known forever. We don't know who originally discovered them. It was probably some caveman that has appeared in a Far Side cartoon at some point in time, okay? But we don't know when they were originally discovered. They've just always been part of the lore of the sky that our species has passed down through each generation, okay? And so you can see all of the naked eye planets here in this picture, and they are called planets from the ancient Greek word. So I don't know how to speak Greek. Is anyone Greek here? Anyone speak Greek? Okay. So it's Greek to you. Yes. Okay. So it's usually written out in phonetics, right? So this is Adler Planetis, right? Aster, for those of you who are gardeners, means star. Little star-shaped flowers are asters, and planetes means wandering. So the word planet literally means wandering star, because when you see them in the sky, they look just like this. They look exactly like the stars. They're sometimes bright, but they don't move in the regular patterns that the stars move with. And in fact, they're not in the same place all the time as the stars and the constellations are. So what are the naked eye planets? I know they're labeled over there in the picture, but what are they? So they're Mercury, they're Venus, Mars, Jupiter, Saturn, and there's the one everyone always forgets. It's also in this picture. Moon's not a planet. Moon's a natural satellite. Ah, the Earth! The Earth is one of the known planets. Okay? But this is an important point, right? In antiquity, up until the time of Copernicus, we never included Earth in that list. It's only when we discovered that the planets go around the sun that we realized Earth should be included in this list. The frontier's always on the move. The frontier always defines what it is that we know, what we think about the universe. Okay? And including Earth in this list is part of that evolving frontier of knowledge. Okay? But you can see it in this picture. See, it's right here. Okay. Okay. The first world ever discovered beyond the Earth was this one. So what are we looking at here? The moon. Okay. And whose sketches of the moon are we looking at? These are Galileo's. Okay. So in 1609, Galileo turned the first telescope to the sky. And there's neat stories and folklore about what he had to do to convince himself that it was showing him real stuff. Okay? But he started looking at all the things in the sky with the telescope. And when he did, he discovered that you could see things through the telescope, a piece of technology that you absolutely were not aware of if you just looked with your naked eye. And these sketches are his first pictures of the moon. Okay, and what he wrote about this, so in 1610, he wrote a book. We have a copy of this book in our collection. Does anyone know what it's called? It's called Sidereus Nuncius, which means the starry messenger. And it is a capturing of all the things he saw through his telescope and an explanation for what they looked like and how they were different than what we all had grown to understand and expect based on what you could see with your naked eye. And so what he wrote about the moon, he said, the moon certainly does not possess a smooth and polished surface, but one rough and uneven, and just like the face of the earth itself, is everywhere full of vast protuberances, deep chasms, and sinuosities. When you look at the moon through a telescope, you see craters, you see mountains, you see canyons, you see rills, you see vast, expansive plains. And to you and I, who have grown up in the space age and who have seen what the Apollo astronauts have seen, that seems completely natural. Of course the moon has craters. Of course the moon has mountains. I've never been exposed to the idea that the moon doesn't. But you have to put yourself back in the mindset that Galileo had, that every single person on Earth had, before Galileo published the Sidereus Nuncius. Okay, so if you go upstairs, you've all seen this. What's this? The moon. It's out in the Rainbow Gallery now. It used to be out in the Moon Gallery. Okay, but this moon globe was also made at roughly the same time as the Earth globe I just showed you. Okay, why is there only half of it?
We didn't know what the other half was.
because we'd never been to the far side. We had no idea. So why would I waste all of that time making a blank back? Okay. Also in our collection, we have small moon globes, which are very cool. Every now and then they bring them out. And if you look at the back of the globe, blank. Nothing there, right? It's awesome because we didn't know, right? It's cool. Okay, but when you and I stand in front of this, we're like, yeah, that's the moon. Look, it's got craters and it's got seas and it's got highlands and lowlands. Okay, but that's not what the moon looks like. If you go look at the moon with your eye, this is not what it looks like at all, which is why people didn't know that it had craters and mountains and canyons. Okay, so let me ask you a question. How far away do you have to stand from this moon globe in our gallery to make it look like the moon looks in the sky to your eye? Okay, so anyone know how big the moon is to your naked eye when you go stand outside? Yeah, the size of your finger is about the size of a dime held out at arm's length. Okay, so how far away from this globe would I have to stand to make it look that big? Not too far, that's a little too far, but yeah, really far away, right? You'd have to stand about 140 feet away. And at 140 feet, you are not going to see any of these things that you and I stand in front of this globe and say, well, of course the moon has craters and mountains. Because far away, without the aid of some technology, a telescope, you can't see those details. Galileo's discovery was that the moon was a place, that it had structure and things that are similar to the structure and things that we can see here on the Earth. And that was mind-blowing to someone who lived in the 1600s, because before that time, the moon was a marble. It was smooth, but not really. And Galileo was the first person to know that. Okay, he discovered some other worlds, okay? So this is actually from a couple years after the publication of Sidereus Nuncius. So this is literally the back of an envelope. And he took some notes here that I want you to pay attention to. So this is, when I see stuff like this, I'm like, of course Galileo was a scientist, because I do this all the time, right? Michelle's like, who wrote on the back of the cell phone bill, right? It's like, I'm sorry, I had a thought, I needed some paper, it was there, right? Okay, so this is some envelope, some correspondence. This is the collection, this is in the collection of the Morgan Library at New York. So if you go to the Morgan Library and you search, you can see this image in full detail and blow it up and look at it. But it's very cool. But what is this that he's sketching right here? This is also something else he discovered. Jupiter and its moons. Okay? So Jupiter was one of the naked eye planets. It was one of the planets known since antiquity. And when Galileo first pointed his telescope to the Jupiter, he saw near it 4 bright points of light. And the first night he's like, oh, Jupiter's passing in front of some stars. That's cool. Okay? And then the next night he's like, those 4 lights are following Jupiter. They're not in the same position anymore, but they seem to be following Jupiter. Okay, and then the next night, those same 4 lights are following Jupiter. Okay, and so he made a series of sketches like this. Okay, so there's Jupiter and these 4 lights. Okay, and they are in different positions at different times of day. Okay, and so he realized that these things were connected to Jupiter. Never before had anyone realized, other than the moon around the Earth, which happened after the Copernican revolution, never before had anyone realized that other planets could also have things going around them. So this is the first time we discovered not just other worlds, but other moons, which often are thought to be worlds as well because they're big and interesting places. Okay, and so what he wrote in Sidereus Nuncius is that there are 4 stars which with different motions among themselves together hold their paths and orbs with marvelous speed around the planet Jupiter, the most glorious of all planets, as if they were his own children. Right? So scientists were poets too, right? Okay, so this was the realization that Galileo had, that Jupiter had its own moons. Okay, but again, I want to challenge you to go back in time and put your brain into Galileo's brain. And let's think about what he was actually looking at. Okay, so have you all seen this? Okay, so this is what you see if you go down to telescopes, to the red telescopes that's behind the marble banister. Probably a fake marble banister, but behind the marble banister. And if you push a little button, the moons move around Jupiter. Okay, and so what you see here, this is my attempt to get the moons of Jupiter here in roughly positions that look like some of the ones that appeared in Sidereus Nuncius. Okay, so this one right here is the best I could do for this one. You see I got the planets, the moons in the wrong order. Okay, and this one right here is roughly this one right here. Not too bad. I was very proud of that one. Okay, I was down there for like 10 minutes taking pictures with my phone through the telescope. Okay, but we know, you and I today know that the moons go around Jupiter. Of course they go around Jupiter. They're in orbits. And what shape are orbits? They're circles. They go around, right? But no one had ever seen this before, right? And so if you just sit there and push that button and watch what Galileo saw, what you see is you see the moons just going back and forth in straight lines. And when they're in front of or behind Jupiter, you can't really tell what they're doing. They, in fact, blend in with Jupiter, really, when you see it in real life. Okay? And, of course, you and I have the benefit of sitting there and holding the button down, and this all happens in the course of about 1 minute. Right? But Galileo had to watch it over the course of many, many nights. And he had to deduce from this motion, just going back and forth, that they actually move around in circles. Right? And if you go stare at that for a little while, and just try and imagine how hard it would be to make that deduction from what you see going on. It takes a huge leap of faith. Lauren.
Do all four of the moons look the same through the instrument Galileo was using? Because, like, Ganymede is huge. Like,
yeah.
It's bigger than Mercury.
Yeah.
So,
yeah.
Could he tell any difference?
Yeah, so I don't know about Galileo specifically. Certainly when I look through my telescope, and if you look through a real telescope, they all appear to be different brightnesses. So it's pretty clear that some are brighter than others, but they're all very easily visible. Modern telescopes, modern amateur telescopes, on a good night are certainly clear, can produce clear enough views that you can tell that they have surface features on them through a large enough telescope. Okay, so through a 20-inch telescope with good seeing, you can tell, for instance, that Ganymede has contrast across it. That's a little ball. And that's kind of cool. Certainly Galileo did not have any capability of that, right? 4 points of light, they might be a little brighter or dimmer, but he didn't know anything beyond that, almost certainly. But I have not read what he's written, and we should, get Pietro to pull Sidereus Nuncius out for us and someone to translate the Latin for us. Can you do that? Don't worry. You can read Latin for us?
Anytime you need this old astronomy, which was mostly...
Gloria.
And also the quality of the telescope.
Oh, yeah.
Improved through the
yeah. So I tell people this all the time, is even through the time of Herschel and, the early 1900s, the telescopes that they could build are not even remotely as good as a pair of binoculars you can buy at Walmart, right? Your view through a pair of binoculars is supremely better than the view that Galileo had. So you can see everything that he saw by going to your couch, pulling that pair of binoculars out from underneath it and looking, right? I mean, your couch will rock back and forth for a little while. That's okay. But you didn't need that couch leg, so. Okay, other questions? Have I been a college student too long? Is that what that is? Okay. Okay, so this is a fun exercise to do, but I find it very exhilarating and instructive to try and remember what it was like to not know, because you and I have been told this and we believe it. But the truth about all of these things about the universe that we've talked about for the last 5 weeks is that they all can literally be discovered on our own if you can just see. And seeing is part of the game. And so it's fun to especially this stuff. The early stuff, you and I can do in my backyard, no problem, right? So it's fun to do that. So the first planet discovered beyond the planets of antiquity was this one. What's this one? Huh? This is Uranus, okay? So this is a picture in infrared. This is the Hubble Space Telescope picture. So you can see the famous rings. So the rings actually were unknown for about 100 years after the discovery of Uranus, but they're very easy to see in the infrared. So in this Hubble Space Telescope picture, they show up. You can see it has cloud structures and storms on it, which are not unfamiliar to those of us who are familiar with gas giant planets. Jupiter in particular shows this kind of features, but Uranus for a long, long time was almost featureless in terms of the way we drew it. But it was discovered in March of 1871 by William Herschel. He discovered it in his backyard in Bath, which is in Somerset in England. Actually, if you read it, says he discovered it in his garden, which, not being a gardener, I translate to backyard, but maybe it really is a garden. But he was observing in Bath at the time, and he discovered this new world. And so he reported it dutifully, and he called it a comet. Okay, now in those days, there were 5 known planets, and people were discovering comets. The way to make a name for yourself in astronomy in those days was to discover a comet. And Herschel saw this, and he knew that it wasn't something that was a star. It was extended, it was round, it was fuzzy. Okay, if you listen to what he said about it, it's pretty clear he didn't think it was a comet, right? Because he talked about it when he made presentations to the Royal Society as if it was a planet, but he repeatedly called it a comet. But as we began to study it more, and once the announcement was made, everyone turned their telescopes to it and discovered it, we began to decide that it wasn't a comet, in particular because its orbit did not look like the orbit of a comet. So what's an orbit of a comet look like? It's elongated, right? It starts far out, it comes in close to the sun, so it's very long and oval shaped. And after you watch Uranus for a little while, you see that its orbit is pretty round, which is what we associated with all the planets. And so very quickly we came to the realization that, oh my gosh, this must be a planet. The 5 planets, 6 planets if you include the Earth, that were known since antiquity are not the only ones. Technology has provided us with the opportunity to discover a new one. And that piece of technology is a telescope. Okay, and we'll talk about that in a minute. Now, Herschel wanted to call it Georgium Siderius. And what is Georgium Siderius named after? King George, right? So King George was very happy with this discovery, right? It's like, oh my gosh, we've discovered a planet. He paid Herschel some enormous sum for those days. It was like 200 pounds a week or a month or something, to move to Windsor and be his personal astronomer. And he would fund Herschel's ongoing and continuing astronomy work with the stipulation that Herschel show King George and his family stuff through the telescope. Okay, it's like Herschel was the first amateur astronomer, right? It's perfect. So he did that. He wanted to call it Georgium Siderius, but of course there was lots of objections to this. Even in those days, astronomy was becoming an international endeavor, and so people did not like the idea that there would be territorial or cultural instances of naming things in the heavens. And so there was a lot of argument about what Uranus should be named. And so actually it was another astronomer named Bode who proposed the name Uranus. And so Uranus was the father of Saturn. Saturn was the father of Jupiter. And so this idea really resonated with people that you should just continue the progression of naming the planets after the Greek gods. And so very quickly the name Uranus stuck. There were a few Georgium Siderius persistences as time went on, and I think it was maybe even into the 1900s before the last observatory that insisted on calling it Georgium Siderius finally relented and started calling it Uranus. But once Bose proposed it, it very rapidly gained acceptance, and we've all been calling this Uranus ever since. Now, down in the telescope gallery, we have one of Herschel's telescopes. So Herschel had, I think, 3 telescopes, just like this one, that he was using at the time that he made the discovery of Uranus. And so he'd switch back and forth between them in his house there in Bath. So we don't know that this is exactly the one he was using that he discovered Uranus, but we're absolutely certain he looked at Uranus through this one. And so it may be the one he discovered with. We're not even sure Herschel knows. But the thing I like to show people about this telescope is that this telescope is not terribly different from the kinds of telescopes that you see people using in their backyards today. Okay, it's very roughly the size and shape of what we call a Dobsonian telescope, which is the most common reflecting telescope that amateurs buy. I have a telescope that my very first telescope was very much like this. I had a slightly different mount, but I had built a hexagonal wooden tube and everything. I didn't even know Herschel had done that. So I'm like Herschel's protege, and I don't even know it. So. Okay, down here you'll see the mirror that belongs in that telescope. So that mirror is about 6 inches in diameter. 6 inches for a long, long time has been the classic size telescope that most amateurs start with when they want to learn the sky. Amateurs, of course, today have much larger mirrors. So my telescope I use every day is 12 inches. My big telescope is 22 inches. So you can get much larger ones than this. But you can see a lot of the sky with 6 inches. And in fact, you can discover a planet using a 6-inch telescope. The next planet discovered was this one. What's this one? Neptune. Okay. Now, this planet was discovered by yet another kind of new technology, and that technology was called math. Right? Everyone laughs, right? But it's true, right? So this guy here, this is Urbain Le Verrier. He was a mathematician who had been studying the orbit of Uranus. Okay, and when you study the orbits of planets, the shape of the orbits are regulated, are governed by the law of gravitation, which we've talked about many times, right? It's this universal law that Newton wrote down, and the reason we use it as a law of nature is because it unfailingly describes, without error, the orbits of things we see in the sky. Stars around other stars, planets around the sun, moons around Jupiter, comets around the Earth, right? There's a very famous story where Newton had worked all this out, right? He had shown that Kepler's laws of motion come from the universal law of gravitation. And, you know, he was Newton. He did it on the back of his cell phone bill from the 1870s, right? And so Halley, who was getting interested in comets, wrote Newton a letter and said, Newton, I know you're busy. I'm sorry if you don't have time. Do you happen to know what the shape of a comet's orbit is? And Halley thought it would take Newton 4 or 5 months to respond to this, and Newton responded instantly. Well, of course, I worked it out 20 years ago. And Halley's like, what? Why didn't you tell me? But he had, and he had worked out that they are very elongated ellipses, okay? Well, Le Verrier was this kind of guy, right? He knew how to do the mathematics of orbits. And when he looked at the orbit of Uranus, there were interesting deviations, what physicists call perturbations, okay? And you can explain those perturbations with gravity. And Le Verrier worked it out, and he said, oh, well, this much gravity is tugging it here, and this much gravity is tugging it here. And I can explain that if there's an unknown planet right there. Okay? So he dutifully wrote this up, sent it around to the world, and astronomers are like, crazy mathematician, ha! Right? But this guy, so this is Johann Galli, he was at the observatory in Berlin. The day after he got the letter from Le Verrier, he put his telescope on the sky, and he discovered Neptune on the 23rd of September in 1846, within 1 degree on the sky of what Le Verrier said it would be. Okay, so 1 degree on the sky is about the size of your thumb. Okay, so Le Verrier said be there, and he found it right there. And those of you who've played with telescopes, that's like just, you kind of bump your telescope and you're there, right? It's not that far away. It was amazingly accurate because math, right? Awesome technology. So who was actually the first person to see Neptune? Does anyone know?
Didn't they think that Galileo actually saw it, but he
Yeah.
didn't know it?
So in December of 1612 and January of 1613, Neptune was a place in its orbit in the sky where it's what we call stationary, right? It had slowed down because of its relative motion with respect to the Earth and was just kind of standing still. And if you look at the sketches Galileo was making at that time, they're almost exactly centered on Neptune. But over the course of that month, it didn't move, and Galileo didn't know it. So he thought it was a star. And it's right there in the sketches, but he didn't know it was Neptune. Okay? And so he's not credited for the discovery. But to the question that was asked earlier, right, this tells you something about Galileo's telescopes. If you and I go out in my backyard right now and we look at Neptune and Uranus through a telescope, it is obvious they are not stars because you can see their blue color and they're round, right? They're big and they have shape to them. They're bigger. You can tell that. But Galileo's telescopes weren't good enough to tell him that. And if they were, he might have noticed that it wasn't a star at all. Okay? But nonetheless, he didn't know, and so he's not credited for the discovery. It goes to Le Verrier and Galli. Questions?
Did Galileo improve the telescope he had through the years?
Yeah, his telescopes, they slowly improved, and a lot of that has to do with the improvement in lens making technology. A lot of that has to do with the improvement of the size of the lenses themselves. So bigger lenses can gather more light and see more. If you go to telescope gallery, one of the things that you notice, for instance, the Saturn telescope is enormously long. right? And so one of the reasons telescopes get long like that is because it's very hard to make accurate lenses. And so if they made them long, their technology for making lenses didn't have to be quite as stringent. But that introduces its own host of problems, right? Namely that it's hard to take that telescope and point it. And so if you see pictures of telescopes like that one, so Huygens is famous for using a telescope like this. They have these gigantic pulley systems, and you gotta get 5 of your friends to go out with you and hoist it up and pull the pulleys and hold them still while you're looking at Saturn, and oh, I'm sorry, you're holding the ropes, you don't get to look, right? So it's not a friendly profession if you had friends who wanted to do astronomy with you. So not like today, where you just point the telescope and it stays there. What I think is interesting about looking at Herschel's telescope is it's clear he's trying to work on how can I accurately point and keep this thing pointed where it is so that I can handle it myself, which of course is the hallmark of the Dobsonian design. It's very, today telescopes are easy for us to handle because they can be pushed and moved very easily. So, okay, other questions? Okay. So here's another possibly familiar story. So there was yet another planet discovered, right? It was initially called a planet, right? But it was demoted eventually after we eventually started to find other similar worlds to this, which of course caused pandemonium in the world, right? But this year it's going to be visited by a spacecraft for the first time. What planet is this? Right, you're right. It's one Ceres. Wait, what? So, in 1801, Giuseppe Piazzi discovered a world between Mars and Jupiter. It had been expected that there would be a world there for a math reason that we now know is not true. Okay, so there's something called the Titus-Bode law, which is this mathematical progression of the sizes of planets' orbits. We now know it's an artifact, it's not real, but it was observationally there. How many of you did the planet folding activity with me last year, where we made the solar system maps by folding paper? That works because of the Titus-Bode law. That folding pattern is the Titus-Bode law. And so if you fold that map out and you follow the Titus-Bode law, you get that there should be a planet between Mars and Jupiter. And no one had seen it, and so they were looking for it. And in 1801, Piazzi found it. He's like, look, there's a world there, right where we expected. Okay, let's call it Ceres. Everyone's like, yay, let's call it Ceres. Let's start looking here, and we'll watch it a lot. Okay, but they started to find other planets in that same area. Vesta, Pallas, Eros, okay? All what we now call main belt asteroids. So this started to freak people out. They're like, wait a minute, there's only supposed to be one planet here, but there's many. And so I think it was Herschel, actually, who coined the word asteroids, which means star-like, right? Aster, okay? And we decided that these things weren't planets at all. But of course, astronomers and scientists had invested themselves in calling this a planet, and so pandemonium erupted, right? And so people were really upset like this, okay? So it was demoted, and of course, Dawn has just arrived at Ceres. For the first time ever, we're orbiting Ceres, and we're getting closer and closer and getting better and better pictures. And does anyone know what the big deal right now on Ceres is? So, bright spots, right? So as we approach Ceres, there's these kind of really bright patches. We had no idea what they are. As we get closer and closer, they're breaking apart. The pictures are getting bigger into smaller and smaller spots, and we don't know what they are. We think they're ice, I think, is the current belief. Yeah. So it's very cool. So pay attention to Ceres. What's special about Dawn? Does anyone know what's special about Dawn? So Dawn is the first spacecraft to be propelled by ion propulsion, which is a very highly efficient, although slow, form of propulsive engine. It's very efficient, very good, and this is the first spacecraft that ever used it. So, okay, but all of you thought I was talking about Pluto. Okay, because of course I led you to think about Pluto, because you and I have forgotten that Ceres didn't used to be an asteroid. We live 200 years in the future, and we're completely comfortable with the idea that Ceres is an asteroid, because we've been told our whole lives Ceres is an asteroid. Okay, but many of us feel very emotional about the fact that Pluto is or is not a planet, because we know deep down in our hearts it is. Pluto and the Adler have a very storied history. Okay, so this is opening day on the Adler, right? This is the 12th of May, 1930. We just had our 85th birthday. But less than 6 weeks before, the announcement of the discovery of Pluto had been made. Okay, so this is the Chicago Daily Tribune. So you can see this online. You can go read the story. Scientists spy planet hunted for 25 years. It's big and cold. Okay, so what do we know about Pluto today? Is it big? No. Is it cold? Yeah. Okay, so frontiers, right? Things we know, things we don't know. This is our ignorance showing through again. Okay, and our ignorance is still strong because apparently Pluto's not a planet. But we can talk about that at some other point. So at the time that the Adler was being built, we didn't know about Pluto. And so we had ordered the plaque that is now on the front wall in the Rainbow Lobby when you first come in. And if you look at it carefully, all the planets are there except Pluto. And so from opening day until 2006, everyone's like, man, this plaque is wrong. Why haven't we got a billionaire to help us fix it? Okay? But then in 2006, Pluto was unfairly and viciously demoted, I might add. Pluto was demoted, and then suddenly the plaque was right. Okay? So we're good. Okay? So anyways, so there's a little interesting history here. The debate about Pluto is actually very serious, and we have serious questions about it. And I've talked about this with many of you before. In fact, I think I talked about this the last time we did the class maybe. But I'm happy to talk with anyone about Pluto if you want to. But Pluto is part of this story as well. And the thing about Pluto that's interesting, the argument about Pluto is really not about what Pluto's status is. It's about what do we mean when we say the word planet. Right? Historically, the word planet means wandering star. It means some bright light in the sky that doesn't stay put like a constellation does. And so if you just take that ancient Greek definition, yeah, by all means, Pluto should be a planet. Okay? But our view of the cosmos has expanded dramatically. And so now we argue about different ideas about what that word should mean. And that's what the whole debate's all about. Okay? So, New Horizons, of course, is the first spacecraft ever to visit Pluto. It will sail by on the 14th of July in 2015. But already it's starting to get exciting. Just about, 3 weeks ago, we're finally what the New Horizons team calls BTH. Does anyone know what that means? Better than Hubble. That means the pictures we can take of Pluto are better than the pictures that Hubble can take of Pluto. And if you've seen the pictures that they've been sending back, they're pretty crummy, okay? But that's why they're better than Pluto, because they're so close now that Hubble's view of Pluto is pretty crummy, because Pluto's so small and so far away. And between now and July, it's only going to get better. Okay, so keep your eyes open. There's going to be a lot of events going on. We're planning events here at the Adler. Kyle and public programs and several of us are starting to talk about this. So there will be things going on. So we'll talk about this a lot when July gets here.
Where Charon is going to be?
Yeah.
Pluto, and is it going to be on the far side?
Yeah. So we have control, right? So we're going to fly through. Right, so we have some control, and that's mitigated by where we want to fly through and where we're trying to get to afterwards, because we're going to use Pluto's gravity to redirect us out into the outer parts of the solar system. I'm sure the flight team has worked this out, but I haven't seen what they're going to do. Okay, if you see the images now, you can see Charon in Pluto, and they're going around, right, each other. And I just read last week that we can now see all 5 of the known moons.
Really?
Yeah, but I haven't seen a picture, but I heard that we can now, which is cool. So technology is the thing that makes all of this discovery go. And sometimes that technology is just bigger, right? So this is my 2 telescopes that I built, right? Okay, so you can build telescopes and see the world better. And today, people like me and you, so this is a habit I have, I'm sorry. When I say me and you, sometimes I mean us, the amateur astronomers. And sometimes when I say me, I mean us, the professional astronomers. So right now, I mean us, the amateurs, okay? People like me and you can go out in our backyard and make discoveries. We find comets, we find asteroids, we can see exoplanets, actually. We can see supernovae. The world depends on people like me and you making those discoveries, because the sky is big and we have way more glass, way more telescopes at our disposal than the professionals have. And you know, they're all busy teaching classes, writing grant proposals, being science folks. And you and I are out every night going, screw it, I could be tired at work tomorrow, I'm going out with my telescope. And we watch the sky, which is why we discover stuff. Part of discovery is always pressing forward and being diligent. And so amateurs have that in spades. Okay? Technology can, of course, build bigger telescopes for professionals. So these are the two Keck telescopes on the summit of Mauna Kea. These are both 10-meter telescopes. There's a lot of debate right now, but it does seem that we're going to build a new telescope in Hawaii that's going to be bigger than the Keck telescopes. Does anyone know what that telescope's called? It's called TMT, which stands for 30-meter telescope. So the Keck telescopes, each one of these is 10 meters. That's about from here over to here. Okay, and TMT is going to be 3 times that large. The TMT mirror will blanket this room. Man, I want to put my eyeball to that telescope, right? That would be awesome. Okay, so technology, bigger, always enables you to see deeper into the cosmos. Sometimes that technology goes to space. So this is a very famous instrument called WISE, the Wide Field Infrared Spectroscopic Explorer. WISE was a telescope that looked at the whole sky in infrared, which is exceedingly valuable when you're interested in things like planets and asteroids, because they radiate very strongly in the infrared. And of course, things like this are enabled by things like this, by rockets. Okay. And what was the first world ever explored by rocket? The Earth. Because the first thing we did when we put a telescope on a rocket was we turned the camera around and we looked at the Earth. Okay, so that globe upstairs was the last view of the world that we had before we started doing this, which is kind of cool. This is a survey of the solar system. This is all 88 known bodies in the solar system whose diameter is greater than 200 miles. Not all of these have been known forever. Many of them have been discovered in just the last 10 years. But as you see, you go from things that we call planets, but eventually you get into this very fuzzy regime. There's a planet, there's not a planet. Okay, there's our satellite, the moon, and down here there's a planet. Okay, you start seeing things that all kind of look the same, but some of them we call planets and some of them we don't call planets. And this is what the whole difficulty in this whole idea that there's a word we use to describe objects in the universe. Because when you look at that progression, it's not clear that all of those things are different from each other. So when I say a word to you, I'm usually mean that I know enough about that world that when I have a set of buckets, I know which bucket to put it in. But if I just handed you any of those worlds with one bucket that said planet and one bucket that said not planet, you may not know which bucket to drop it into. Okay? Because just taxonomy based on visual appearance is not enough. You got to start looking at more than that. Okay? So this is the solar system. And up until the mid-1990s, the late 1990s, everything that we thought about planets and planetary systems was based on what we could see in the solar system. And the argument about Pluto in particular is based on what we know about the solar system. And it's because when I look at the solar system, it has this very nice structure. I can divide the solar system up into groups, into neighborhoods, as we would say in Chicago. Okay? And so this neighborhood near the sun is what we call the terrestrial neighborhood. What's terrestrial mean? Rocky or Earth-like. Okay? So this is Mercury, Venus, Earth, and Mars. Small worlds that are mostly comprised of rock. They often have molten or metallic cores. Okay? But they're rocky. That's mostly what they're made of. Terrestrial, they're Earth-like. These worlds, this neighborhood, is called Jovians. What's Jovian mean? Jupiter-like, or what we call gas giants. So these worlds, they down in their cores have rocky cores. Jupiter has a 10 Earth mass or 15 Earth mass rocky core. But most of the world is comprised of gas. And that's true of all 4 of these worlds in this part of the solar system. And then out past Neptune, where Pluto lives, is what we call the third zone. It's kind of like the Twilight Zone, right? It's out there where things are weird and we don't really understand stuff. Because We haven't ever had the technology to get out there until today. We have telescopes that can look out there. We're finally, at last, sending spacecraft out there. So we're going to know more. But in the third zone, it's quite clear that these objects out here aren't like these objects. We're pretty sure they're not like these objects, but it's unclear why and if it's universal. So what are things out here like? Does anyone know? They're icy, right? They have a lot of rock in them, but they typically have more ice and what we call volatiles, things that would evaporate if they got closer to the sun. And so that's the characteristic, together with the fact they're on wonky orbits, of what things are like out here in the third zone. When I say they're on wonky orbits, most of the stuff in this part of the solar system is very close to orbiting the sun in the same plane as the Earth. Okay? Things out here, Pluto in particular, orbit on orbits that go like this. Okay? So that's what we mean when we say wonky orbits. Dario.
The regular planets, they all had the same origin. They were
Yeah.
formed
Yeah.
at the same time.
So let's talk about that. Let's talk about origin. This is exactly the point, right? Is that our ideas about planetary systems come because we see this picture, and this picture has led to this idea about the origin. So let's talk about that. That's a great question. Okay? So we saw this last week when we watched the movie of the Orion Nebula. You remember we flew by that star, which they said had this faint dusty disk building up around it. I can't remember the name of the star. So when a protostar forms, it's because in the giant molecular cloud, somewhere in that cloud, there's a little bit more. And when there's a little bit more, the gravity's a little bit stronger, and it pulls stuff towards it. And when it pulls stuff towards it, the gravity gets stronger and it pulls more stuff to it. And it just keeps piling and piling and piling stuff on. And it grows dramatically until such a time that there's so much gas and dust pressing down on top of it that down in the core, nuclear fusion begins. Okay, and that's when you get into the formation of stars. And we've talked about that a little bit. Okay, but the growth in gravity continues to attract matter towards this protostar. And as matter falls towards it, not all of it's falling directly towards it. Some of it's trying to fly this way. And so if I'm falling towards this because the gravity's trying to tugging me to my right, and to my right, and to my right, and to my right, and I start going around in a circle. Okay? So as I fall in, if I'm not shooting straight at the source of gravity, it's going to make me go around in a circle. Okay, and how many of you make pizza? Yeah, make your own pizza dough at home? Yeah, and do you throw it? Do you throw your own pizza dough? Oh, you don't? That's right, because otherwise it'd be stuck on the ceiling, right? Okay, but when you throw out pizza dough, if you go to a pizzeria and watch them do it, what do? They spin it, and what happens to it? It flattens out, right? And that's exactly what we see happening here. So we call these things protoplanetary disks. The stuff naturally flattens out into a disk-like shape. Okay, and so physics, right? That's why that happens. If you want to take physics from me, we can talk about why it is. Those of you who remember physics, you can go read all about angular momentum, and you can learn all about it. Okay? So in that disk, the exact same thing that happened to form the star is happening on a smaller scale. There are little regions where there's more stuff than in other regions, and the gravity there is a little bit stronger. And so it pulls more stuff towards it, and they stick together. And the gravity gets a little bit stronger and pulls more stuff to it, and they stick together. And so you start seeing all of these little things forming, and we call these planetesimals. Now, over time, right, these planetesimals get bigger and bigger and bigger. Okay, so this whole thing starts spinning out, and this is probably closer to the stage that we saw in the video last week, okay, what we call the protoplanetary disk. But as these planetesimals start to grow and get bigger, you begin to see openings showing up in the disk. And that's because this thing here that's growing has been sweeping up, has been gathering all of the stuff that's in its way and clumping it on top of itself and getting bigger. Okay? Eventually, the star's light and the planets are going to clear out most of the molecular gas and dust that was there. The planets will either suck them up onto the planet, or the star, as it gets brighter, the stellar winds turn on, the energy from the light blasting out heats up these particles and pushes them outward, just like the light sail that the Planetary Society is building right now. Do you guys know about this? Right? Okay, same thing. Okay, the pressure, the light, can push all these small particles outward. And so it begins to clear the solar system, the planetary system, of gas and dust. And you're left behind with planets and then big things. And what's going to happen with the big things? They're going to crash into everything that's left. And so we see this in the geologic record in our solar system. This is a period that we call the late heavy bombardment. It's what created most of the craters on the moon, large craters on Mercury, the kind of cratering that we see still persistent on Mars, the big stuff at least. Okay, this all happened because as the planets go around, every now and then they still encounter big things. And that still happens today, just not at the frequency that it used to happen, right? It's like walking through a swarm of mosquitoes, right? In the middle, it's really dense, but once you squash them all on your windshield, then there's only a few left. Okay, so we're in the post-windshield squashing phase of the solar system.
Is there a preference in nature on which way the protostar spins, clockwise, counterclockwise? Is there?
Yeah, so that's a good question. So there, if you look at something that's, say, spinning clockwise, but then you stand on your head, it will look like it's spinning counterclockwise. Okay, so what you and I call clockwise or counterclockwise, there's no preference for. A more interesting question is if I look at a much larger scale, like say the scale of the galaxy, is there a preference for alignment with the galaxy? And I don't think we know the answer to that question yet because we don't know of enough planetary systems to know. I think most astronomers will tell you no. But I'm a very firm believer in, okay, you can believe that, but show me some data that proves that. And I don't think we have enough data yet to prove that. Okay, that's an excellent question though. Other questions? Yes?
When the planetesimals get cleared out,
Mm-hmm.
I mean, we still have the big remnant, right? The asteroid belts.
Yep.
Is that eventually going to get cleared out? Like, will
Yeah.
Vesta and Ceres get bigger?
Yeah.
And will that eventually, or Jupiter suck more things and become more
Yeah.
moons, or the
Yeah.
sun, and they'll, like, when, and if so, when will that happen? And also, if it does happen, could then Ceres be considered a planet? Because it will have cleared out its orbit and it would have gotten a little bit bigger. Maybe it's like mighty enough.
That's right, right? So those are excellent questions, okay? And the question of clearing is always a question of timescale, okay? So Ceres and all the objects in the asteroid belt, there are collision timescales that we can compute when they will hit each other. But it's very long right now, and it's long compared to, I mean, they happen, what, every 10 million years or something, right? But if I compute the total length of time left in the solar system, it's probably not enough time to clear out the asteroid belt before the sun dies, okay? But your question's an important one, because this thing about clearing your orbit is crazy. That's why most of us argue about this, right? Is that the idea that you're a planet or not a planet based on what's going on around you is silly, right? That's like saying, you're Lauren right now, but as soon as you walk out the door, because you're not with the rest of us, you're a platypus. That's silly, right? It should be, whether it's a planet or not, should be something about its physical characteristics. Something I can say about it and not about what it's doing in relation to everything else around it. And that's what we argue about. One of my colleagues in Arizona who thinks about this a lot, he tells the following story. He said, if you could put Jupiter out in Pluto's orbit at the time the solar system formed, today, Jupiter would not have cleared its orbit yet and would not be considered a planet. That's crazy.
Is it just because there are so many?
It's because it's so many things and it takes so long for it to happen.
Well, I guess then that brings up a question for me with comets.
Mm-hmm.
Like if you plucked a comet out of its orbit and just stuck it in a line,
Right.
What would we call a comet?
Right. So this is right. A comet physically, its physical characteristics, its composition, its makeup is different than a rock I can pick up outside the Adler. It's got lots of volatile ices in it. It's got primordial ices in it, and it is not the same thing as a silicate rock that I pick up here on Earth. Right? A comet is a tiny enough body that its gravity is not strong enough to make it spherical. Neither are many of the asteroids. Okay? And so these are things about the physical characteristic. And so when we have conversations about what do you mean when you say planet, these are the things that we really want to talk about. And Mike Brown and the planetary scientists who are on the side of Pluto not being a planet, this is actually what they're concerned about, and rightly so. Pluto's composition is not like the composition of stuff in here. Right? Pluto's composition is like the stuff that's out in the third zone. And so whatever that stuff is and whatever it's going to be called, Pluto very rightly should be gathered together with those things. But the definition you're using to group it with those things right now is just garbage, right? That's our objection.
When early stages of the solar system, wasn't Jupiter closer in and moved farther out?
Yeah. So this is something we don't know. So we see this in other solar systems. So we're almost out of time here. So we'll blaze through exoplanets and we'll say this. But when we look at exoplanetary systems, we see planets like Jupiter in all kinds of different orbits. And the frontiers of planetary research right now are trying to understand how do you move something the size of Jupiter around in a solar system. Yeah, and there are lots of ideas. We're not sure which of them are right, or if many of them are right and some of them are wrong. This is active research, and we do this research here in Chicago. There are folks at Chicago and Northwestern both who do this sort of stuff. Yeah. Okay. So in the end, we see long-lived, stable planetary systems, just like the solar system. Okay. So this is the end of the evolutionary story, but this is just one example. Okay. And the most amazing thing to me is that if I want to know more about planets, I can't just base everything I think and everything I know on this one planetary system that I know about. Okay? Oh, the Oort cloud. Right? So this is the third zone. So all the stuff that's left over from that formation story that I just told you about, this thing we were just talking about, the time scale over which it takes things to grow and develop is far outside the boundaries of the orbit of Neptune. Okay? And so there are probably 1 trillion icy bodies. That's a 1 followed by 12 zeros out in that part of the solar system. Okay, so there's a lot. So this isn't the whole story, because if I want to know more about the universe, I can't base everything I know or everything I think on this one planetary system. And despite the fact that for the last 100 years, Hollywood and George Lucas and Gene Roddenberry and all of those folks have been telling us that there's other planets, that's not the same thing as knowing there are other planets. So if I want to talk about planets, I have to look for other planetary systems. And the most awesome thing to me, the thing that just blows my mind every single day and makes me so happy to get up in the morning, is that you and I are living in the age where for the first time ever, we know that there are planets around other stars. Before the 1990s, we had no freaking idea. No matter what George said, no matter where Captain Kirk and Mr. Spock and Lieutenant Uhura went, we didn't know. But today we do. Okay, so a lot of that story is tied up in this satellite. This is called the Kepler satellite. And so Kepler has been up for a couple years now. And for the first couple years of its life, it was staring at this part of the sky. So we've talked about this part of the sky before. This is Cygnus, the swan. Okay, and the summer triangle, I've kind of cut the bottom of the summer triangle off right here. But roughly halfway between Deneb and Vega, Kepler has been staring at this part of the sky. And so what it's been doing is it stares at that part of the sky and it just measures the brightness of every single star in that area. And if a planet happens to go in front of its star, the light from that star will go down a little bit. And when the planet comes out from in front of the star, the light goes back up again. We call that a transit. Okay? Now we've seen transits here on planet Earth. How many of you have seen a transit here on planet Earth? Okay? When? Venus, right? 2 years ago. How many of you saw the Venus transit? Anybody? Okay, a few of you. Okay, so this is my picture that I took of the Venus transit. Okay, here's the sun, and Venus passed right through the center of the sun, meaning between me and you and the sun. And if I could measure the overall brightness of the sun, which is what I'm doing here by taking a picture of it, when Venus is there in front of the sun, the light from the sun dips. It goes down. It's like holding your hand up in front of a bright light. And then when you move your hand, it gets bright again. You're standing in the shadow of Venus. Okay? And so Kepler does this by watching the light from stars. Okay? So this is from 12 hours to about 17 hours. And when a planet goes in front of the star, you see the light from the star go down, and then the light from the star goes back up when the planet comes out again. Okay? And we discover all kinds of crazy planets this way. We discover planets like this, okay? So this is called a hot Jupiter. This is a planet like Jupiter, but it orbits 10 times closer to its parent star than Mercury does to the sun. It goes around its parent star in like 8 days. Okay? That is not a fun place to live. Okay?
We think it's gas.
Yeah, it's gaseous, yeah. But it's being blasted apart by the star, right? It's being evaporated. But yeah, it's gaseous. We can tell that. Okay? Okay, we see planets like this. Okay, so George in Star Wars introduced us to a planet around 2 suns. What's that planet called? Tatooine. Yeah, here's a planet that orbits 2 stars. We see them. Hollywood got it right. It was awesome. Okay? But we're still a little confused. We're not quite sure how you make them, how they stay stable. Okay? There's still open questions there. That's the frontier. We see planets around stars smaller than our sun. When we talked about the main sequence of stars last week, do you remember what kind of star the sun was? G, right? Oscar bought a fancy garbage can Monday. So Monday, M stars are little small, what we call red dwarfs, and we see lots of planets around them. Okay? They're probably the most common types of stars that have planets in the universe. We set out looking for planets around stars like the sun, but this is where we find most of the planets, which is kind of interesting, right? Okay, so this is called the Kepler Ori. This is a representation of all the planets Kepler had discovered until about 2013. So the planets are, the spot size is about the size of the planet, and they're going around their orbits at approximately the right speed, and they're colored based on how far away from their planet they are. Okay, so you can watch this movie, it'll be on the slides, but it hurts your head. But the cool thing is that there's lots of what we call multis. Okay, so this has like 7 planets in it. Okay, so this is not unlike our own solar system. And when you look at the Kepler multis, it's not clear that they look like our solar system at all. So that whole story about terrestrial worlds, Jovian worlds, third zone, maybe it's right, maybe it's not, which is kind of funny. Okay, so of course we look for planets here at the Adler. So if you do Zooniverse stuff, you can look for planets at Planet Hunters. If you're interested in all the exoplanets that we know, you can go to the 2 exoplanet encyclopedias online. There are very nice interfaces for your phone there that show that. Okay, and so I'll leave you with these last thoughts, right? So I told you this. This is the most awesome thing in the world. You and I are living in the age of planetary discovery. This is what it was like when Herschel and Galileo and Leverrier first discovered new worlds for the first time. But it happens every single day. And so it's commonplace to us. You and I are like, of course we discover planets, right? And we can't remember what it was like to live in a time when we couldn't discover planets. Okay? So I told the class on Monday this would happen, so it did. Every time I looked this number up, it changed. Okay, so on Monday, there were 1,921 known planets. Today, there are 1,924. Right? Okay, there's like 4,000 that we think are there that are what we call unconfirmed. We haven't followed them up. So, okay, and as always, we had this argument. We're just learning what we mean by planets. We're not sure yet, but we'll figure it out soon. Okay, these are very good books to read. I have not yet read any books about exoplanets. These are all books about Pluto. This book is clearly wrong. This book is kind of about history, but it's clearly wrong. Alan gets it right. So no, I'm kidding. These are all great books. Mike's book is, as you can imagine, very entertaining because Mike has opinions about this. Neil's book is very nice because it tells the history, the whole Pluto history, and so you can read about it there. And Alan is very much on my side of the story, and he makes a very nice case for why this should be included in planets. Mike gave a very nice lecture. If you didn't see Mike's lecture here at the Adler, the Keck Keck Institute has a lecture he did based on this a couple years ago. This is a very good talk to talk about, and I did a TEDx talk about this last year about Pluto, so you can watch that online as well. Okay, so I said I didn't care if the president came in, but I do, so I'm going to call it a night. So, okay, thanks everybody.